So I'm going to talk about a line of work that I've been doing now for, I guess, a decade or more, thinking about the problems that human listeners face when understanding speech, not in the optimal situations that we mostly study in the lab, but the degraded situations that we encounter in our everyday life. Now, one important motivation for this from my point of view, and indeed from the point of view of my funders, the Medical Research Council in the UK, is to think about individuals with hearing impairments, individuals who use hearing prostheses, and the challenges that they face. So here's a picture of a happy child using a cochlear implant. So the cochlear implant is the most successful neural prosthesis in the world. So there are approximately 500,000 people in the world who, like this girl, gain a functional sense of hearing and would otherwise be entirely deaf. So the exterior part of it looks a bit like a hearing aid. So you have a microphone connected to a signal processor. What's different is that instead of amplifying sounds and playing them into the ear, the sounds get passed to a kind of plastic plate that you can perhaps see hidden in the girl's hair. And then what happens is that electrical impulses are sent across the scalp and into a receiver that then passes electrical impulses directly into an electrode array inserted into the cochlea, stimulating the auditory nerve. Now this, as I say, provides functional hearing, and a good outcome for someone using a cochlear implant is that they'd be able to have a telephone conversation, so they can understand speech solely based on auditory input. Now where they struggle is in the everyday situations in which we find listening more difficult, so they find it hard to segregate attended speech from background sounds. They struggle to deal with reverberation and other environmental challenges. Their perception of music is also impaired. Now, what we might want to do in the cochlear implant is obviously to improve the transduction of sound. I'm not the person to talk about how you go about doing that. What I'm interested in, though, oh, sorry, actually, before I do that, I'm just going to put in a plug. If you'd like to understand more about cochlear implants, there's a really nice video, Hearing But Not As You Know It, made by an undergraduate in Oxford who uses a cochlear implant in her day-to-day life. I've just tweeted the link to it, so you should be able to find that. Now, what you might want to do is to improve outcomes for cochlear implants. Now, obviously, the first and easiest and probably the most effective way of improving outcomes, improving speech perception for these people, is to make the signal clearer or the background noise quieter. So, you can give a little schematic of what that might look like. So hopefully for you, this word is easier to perceive than these. The signal to noise ratio is better. There are physiological limitations that cochlear implant manufacturers are starting to run up against. And so from the point of view of my research, I'm interested not only in how you improve signal transduction, but also what other factors could improve perception. So two other factors that I think are very important for human speech perception is, first of all, to provide some relevant prior knowledge of the content of speech. And the third one is to try and help the perceptual system, to adapt the perceptual system to a signal that's otherwise degraded. My talk today is going to go through those three mechanisms in turn. So I'm going to start by the most obvious manipulation, so making the signal clearer. And I'm going to do that working not with cochlear implant users, but with normal hearing individuals of a sort that we can very easily recruit, pay a small sum of money, put them in a scanner, and so on. That is our typical young, healthy adult volunteers. Now, what we can do for these participants is obviously not give them a cochlear implant, but play them a simulation that captures the kind of information that's transduced by a cochlear implant and captures the kind of information that's lost. And that's something that's done using a vocoder, a vocoding technique originally developed by Bob Shannon and colleagues. And it's basically a method for reducing the amount of spectral detail and the temporal fidelity of speech reproduction. So you take the spectrogram of a speech sound, of a sentence here, you divide it into a small number of channels, here 6 channels. You extract the slow envelope fluctuations in each channel and use that to modulate a band of noise. You put that together, what you get is a noisy, degraded version of the original spectrogram. What does it sound like? Well, have a listen. That again. That's pretty bad. It's hard to understand. Anyone get anything of that?
Lunchtime.
I'll give you some clues later. So let's move on. Now, one of the things that we can do with this vocoding technique, which is it's turned out to be very powerful and flexible in our experiments, is to change the parameters of the vocoder, change the number of channels, change the envelope extraction, change the signals that the envelopes are superimposed on to conduct different perceptual experiments and indeed brain imaging experiments. So one of the first experiments that we did, working here with Ingrid Johnsrud when she was a colleague in Cambridge, was to just manipulate the intelligibility of these vocoded sentences in a parametric way. So you either hear a sentence that's very severely degraded,
Although extremely tired, she swams strongly.
Or you make it clearer.
Although extremely tired, she swam strongly.
So we've got, actually only played 2, but we've got 3 levels of degradation for which typical participants will report 20, 65 or 90% of the words in an example sentence. And we have 2 other, so that's changing the intelligibility of the signal. We have 2 other forms of distortion which I won't have time to play you today. But these are 3 different ways in which you manipulate the sounds of speech. Then we run an fMRI study, collect a bunch of fMRI data and analyze it. In this case, looking for brain regions in which you see a correlation between the amount of words that people understand and the bold response that we measure with fMRI. That's what's shown here, painted onto a left hemisphere. So you can see this swathe of activity in the left superior middle temporal gyrus, a more confined area on the left. What I've done is paint over that a colour scale that indicates not sensitivity to intelligibility, but sensitivity to the auditory properties of the stimulus, so which of the 3 kinds of distortion were applied. And what hopefully you can see is a kind of graded pattern where areas that are close to primary auditory cortex are sensitive to the way in which the speech has been degraded. And as you go further forward, so ventral or dorsal pathways radiating out of auditory areas, start to show reduced sensitivity to the acoustic properties of the speech signal, but remain sensitive to how much you understand. So this is consistent with the kind of hierarchical organisation that Josh showed very clearly in his studies. Now there's a bunch of other studies that we've done along the lines of this work, but I'm not really going to explore that in so much detail. What I'm going to focus on instead is the response that you see if you look in these inferior frontal regions here, which is a response that shows a correlation with intelligibility, but also shows something of an inverted U-shape. So the inverted U-shape is that the response is actually lower for speech that's fully intelligible because it's clearly understood, relative to conditions like these, which are sort of moderately or highly intelligible, but very noticeably degraded. And we think of this as a neural correlate of listening effort. So those situations where you have to struggle a bit to make sense of what someone's saying, you're listening that bit harder. And indeed, when we go looking for those inverted U-shaped responses, we see them in temporal lobe areas, in inferior frontal areas, and all the way back into here, regions of motor cortex, so brain regions that would be classically associated with speech production.
The fact that you listen to only 6 channels and it is noise vocoder, how can we generalize from that to speech, full speech, normal speech, with periodicity involved and so on and so forth?
Generalize in what sense? I think the participants understand. It's not apparent in this data, but I think in other data, if you compare clearly heard speech that's got all of the periodicity that's missing from the vocoded speech to these forms of degraded speech, the activation maps are largely overlapping.
Quick, is this left or right or both?
Oh, sorry, I've showed the left hemisphere here. At least in the temporal lobe, the activation pattern is largely symmetrical and bilateral. So the inferior frontal regions tend to be more left lateralized. The same is true for some of the posterior temporal, inferior parietal regions. I'm going to keep moving on if that's okay, because I'm going to run out of time if I don't. Now, this listening effort response is something that we see in a whole range of different challenging listening situations. I'm not going to have very much time to take you through it. One of the key things is that it's only really observed during attentive listening, so you have to instruct the participants to pay attention to the speech. Helps if the speech is meaningful for them. And Jonathan Peele and various others have been trying to kind of break apart these different additional activations for degradation into different kinds of functional networks. Now I'm going to focus on the motor activation for a short period now, and take you through a study that looks to establish what kind of neural representations are in those premotor responses to degraded speech. And the technique that I'm going to use is one that's borrowed from my colleague Nico Krieger's court. It's representational similarity analysis. I'm just going to take you through a little cartoon sketch of the method. So like the study that Josh just reported, you record neural responses to single items. In this case, looking not at single voxels, but patterns, activation patterns over small patches of voxels. So in this case, spatial searchlights that we're going to move over the brain. So you compare the activation patterns for two items using a dissimilarity measure, in this case 1 minus correlation over voxels, and you insert that correlation value into a matrix. So for each of the pairs of stimuli in your experiment, you generate a similarity value. Then you can start to test hypotheses about the structure of the neural representations that you express in terms of similarities. So one of the things that you might infer from looking at this matrix is that faces produce a largely similar pattern of activity, houses produce a largely similar pattern of activity, and faces and houses are different from each other. Now you can express that as a predicted dissimilarity matrix, so looking for searchlights, looking for locations in the brain that show this sort of categorical organization. So is there a correlation between the observed dissimilarity of the response to different items and the similarity that you predicted beforehand? So this method is one that we think is very productive. Nico has used it to a very great extent in studying object perception, and we're going to apply it to speech. So this is work that was led by my former postdoc, Sam Evans. Sam didn't present pictures, he presented isolated syllables. In this case, one of 6 syllables, bar, dar, ma, na, arb, and ard, that he presented in one of 6 forms of speech. So a 2x3 crossing, either a male voice or a female voice, crossed with clear speech, vocoded speech, or sine wave speech. So the listeners were trained so that they readily identified both the noise vocoded and the sine wave speech as spoken syllables. Now when we scan these listeners, they're doing an attentive task. They have to detect occasional repetitions of some of the syllables. We get the usual kind of bilateral STG network extending into inferior frontal and precentral gyrus regions. A network that largely overlaps, but with a slightly different emphasis, so a temporal lobe emphasis rather than a motor emphasis for brain regions involved in speech production. And if we do the same contrast that was in the previous study, so comparing the response to degraded speech compared to clear speech, what you get is an elevated response in inferior frontal and motor regions. And that response correlates with individual participants' abilities at monitoring, listening attentively to these degraded speech stimuli. So we think that this motor response is functional. It's involved in listeners when they attend closely and work hard to make sense of degraded stimuli. What kind of representations might these regions have, though? So this is where our representational analysis method comes in. So we have 2 different models that we're going to test against this data. The first is a model that's testing for representations of acoustic form. So we look for similarity between clear speech and clear speech between noise-vocoded speech and noise-vocoded speech, between sine wave speech and sine wave speech. So similarity that's in the surface form of the speech, but we exclude similarity that's due to the syllables being identical. Compare that to a model in which we're looking for representations of syllable identity. So now the diagonal is colored to be similar, so bar should be similar to bar, but dissimilar to all of the other syllables and so on. And we look for that representation irrespective of the surface form of speech. What you can see is that those acoustic and identity representations overlap in the temporal lobe. But when it comes to the precentral gyrus, what you see is a representation of syllable identity without any representation of the acoustic form. So we think that this area is not only active during challenging speech perception, but it's doing so in a way that represents the identity of the syllables that you're hearing and potentially contributes to perception. Past the next result and just summarize that first section. So we think this inverted U shape reflects neural responses associated with listening effort, and the response pattern represents syllable identity, and we believe is playing a functional role in the perception of degraded speech. The second part of the talk is going to focus not on the kind of bottom-up manipulation of signal clarity, but a manipulation of the higher-level knowledge that listeners have at particular points in time. And so I can give a cartoon sketch of that. I like my coffee with milk, but not. One of those words is perhaps easier to perceive, perhaps more predictable in the context of that preceding context. Well, so this isn't news. You know, Bayes' theorem would say that the probabilities are a reflection of the prior as well as the likelihood. That's widely acknowledged as a compelling theory for human spoken word recognition. It's also the foundation of all machine speech recognition. Now, one thing that I think is interesting and different about the way that machine recognition has typically worked and the way that we believe human recognition works is essentially how you combine different levels of representation in the recognition process. So I'm almost embarrassed to put this up in this audience. But this is a kind of sketch of a traditional ASR system in which a key role, sorry, my pointer is not, well, this Viterbi search process combines an acoustic model, a lexicon, a language model. You put everything together and try and maximize probabilities for the word sequence that you're identifying. Whereas in human recognition, we think about a hierarchically organized system. We think about a system in which these representations are interdependent and information is passed forward through a sequence of processing stages and potentially passed backwards as well. Now, one way of capturing that in a neural network kind of way is the trace model of speech perception. So this was published in Cognitive Psychology about 30 years ago. It also featured in the 2-volume PDP books that were such a great inspiration for me, but also for, I think, many of the deep neural network pioneers in the room. Now, if you think about the way that trace breaks up the recognition process, it's got this hierarchical organization, so mapping from acoustic features to phonemes and then on to words. But it also has connections within the layers that implement competitive selection. It has bidirectional connections, so there's a settling process by which different perceptual hypotheses in the form of unit activations compete against each other, and information is passed between the layers to kind of settle into a stable state, such that words are recognized whilst activating their constituent phonemes and supporting the appropriate features. Now, this model remains actually one of the most successful models for the behavioral aspects of human speech perception, so it probably explains more perceptual data than nearly anything else. But I'm going to hopefully persuade you in the next 5 minutes or so that actually the interactive activation part of this model is perhaps not the right way to construe human speech perception. And one of the inspirations for this is the idea of predictive coding. So prediction is very difficult, especially about the future, and prediction is seen as being one of the core processes that neural circuits come to implement. Now, there are neurophysiologists, computational people who are much smarter than me, who generate very complex and elaborate predictive coding schemes. I'm going to take a very simplified view, and I'm going to reduce predictive coding to an equation that even a humble psychologist like me can understand, which is this very simple notion, corresponds in many ways to something that Bob McMurray was presenting yesterday, which is that you take what you hear, you subtract from it a representation of those parts that you predicted, and you compute based on that a prediction error. And so there's this very natural sense in which this equation embodies the combination of sensory input and prior knowledge, and that these prediction error signals are the feed-forward signals that the brain passes forward up a perceptual hierarchy, and signals that we can potentially measure using MEG or fMRI. Now, just to illustrate that, I'm going to play you the vocoded speech again. Now, I don't think many of you got a good percept of that sentence the first time I played it, but if I tell you that it was the man read the newspaper at lunchtime, I'm giving you a perfect form of prior knowledge. It should sound quite a bit clearer. Strikingly clearer when you know what's being said. Now, this reflects that kind of top-down influence of prior knowledge. Now, one of the bits of work that Ed Sahoglu here did in his PhD was to try and quantify the strength of that effect of prior knowledge on perceptual clarity. So what Ed did was to work not with sentences, but with single words. So you'd read a word like clay, you'd then hear it in degraded form. Compare that to situations in which you had mismatching text. So you'd read snail and then hear a different word, or you'd see a row of X's and then hear a degraded word. Now, in order to make the participant's task is to rate the clarity of the spoken words. And in order to make that a meaningful task, Ed also manipulated the amounts of sensory detail in the signal. So 2 channels, 4 channels, or 8 channels. So manipulating the amount of physical detail in the speech. Now, as you might expect, if the speech is physically clearer, people rate it as being physically clearer. But you can get exactly the same benefit if the speech follows matching text. So it's equivalent to doubling the number of channels in the vocoder. The question Ed asked was, what happens to the neural response in these 2 cases? So Ed's using, in this case, simultaneous MEG and EEG. So it's another brain imaging method. In this case, a method like data that Perceptual reported, where you get much better temporal resolution to track the brain response to speech over the time course of a word, as well as some spatial information about the neural generators of those responses. Now, starting with the manipulation of sensory detail, so comparing 8 channel to 2 channels, so speech that's physically clearer compared to less clear, what you get is a response in lateral temporal regions, here shown on the left, though it's actually bilateral. In particular, in these later time windows, you get a stronger response the physically clearer the speech signal is. So in many ways, that corresponds to the fMRI responses that I showed earlier. And what's striking is that if you compare the response following matching trials, so a manipulation that gives you the same perceptual effect, you get a very different kind of neural response. So now match trials, so speech that follows matching, that matches the text that came before, you an increased response in frontal regions, and actually a decreased response in temporal lobe regions. And I'm going to show you that once more. So here in the superior temporal gyrus, so those areas that respond to more intelligible speech, you get an increase in response for speech that's physically clearer, and a decreased response for speech that sounds clearer because it matches prior knowledge. And one way of thinking about that is to say, well, the neural response we're measuring is a correlate of prediction error. And so if you increase sensory detail, you're increasing the left-hand side of the sum, and so you get a bigger response. If you make prior knowledge that corresponds to what you hear, you're making correspondence between what you heard and what you predicted, and that reduces prediction error and reduces the neural response. Now, this makes good intuitive sense, but perhaps there are other computational models, other explanations of that pattern. And in a follow-up study, Helen Blank and I tried to pull apart those alternative computational accounts in a bit more detail. I'm going to try and, so I'll start by just explaining the conditions in Helen's experiment. It's very much the same as the conditions in Ed's study. So you have written text followed by a gap, followed by a spoken word, played at either a low or a high level of degradation. Or they don't really need to play. You've heard enough Vocoded Speech now, I think. Or you see a row of X's followed by the same spoken word. Participants' task is to listen, read and listen attentively. Part of what makes them listen attentively is to have occasional trials in which the correspondence between the written and the spoken is imperfect, like these trials. We also have occasions where they only see a word and have to report that aloud. Now, the critical thing that Helen did was to try and build computational models, very simple, trace-like computational models that recognize degraded spoken words. Now, I'm going to give you a cartoon sketch of the two alternative theories that Helen implemented. So the first one is a model that works in a similar kind of way to trace. So rather than subtracting your predictions, you use those predictions to enhance perceptual representations, to sharpen your representations of the speech signal. So I'm going to give you a sort of cartoon sketch of what that might be like. So if you see a degraded signal or a clearer signal, your perceptual representation is a relatively direct representation of that. If you have some prior expectation for the form of that signal, well, you would use that to amplify or strengthen the expected perceptual components. And so actually what that does is to kind of clean up what would otherwise be a degraded signal. Now we can actually implement that in a computational model. Again, now rather than kind of text strings, we've got distributed vector representations of a degraded or a clearer sensory signal that you multiply by a prior expectation that to some extent corresponds with those sensory signals. The prediction would be that if you're trying to decode those perceptual representations, you'd do better if the sensory signal was clearer, so the lines go up. But you'd also do better if you had some matching prior knowledge. So those representations should be more effectively decoded if you have some matching prior knowledge. Now we can compare that proposal to our prediction error model, where instead of adding or multiplying by your predictions, you subtract your predictions. And actually what you get is something slightly different. So in the neutral case, you're not subtracting anything, you don't have a relevant expectation. But in the case where the sensory signal matches, actually you get a form of sensory cancellation. So a clear signal will be cancelled out in the case where it matches what you expect. And I can show you that in the kind of vector form as well. So for a clear signal that matches your prior expectation, you subtract one from the other, and you get very little prediction error. And so you'd have very little information in the neural representations. Now Helen did quite a bit more than just kind of cartoon sketch these accounts. She actually implemented them in the form of very simple toy models that take a distributed feature representation of speech based around sets of articulatory features that we degrade to capture the degradation of vocoded speech. Maps onto an intermediate representation that's constrained by a top-down signal that comes from a lexical representation. So in this case, it's a 24-way choice output based on the 24 words that are used in the experiment. Helen built two models, both of which have the same input and output representations, both have top-down information flow. But one of them implements this sharpening account where you amplify the expected features. The other uses this prediction error. You subtract the expectation from the sensory input. Now, otherwise, they both operate in the same way. We optimize their parameters. They're not learning models. We give them a kind of static weight matrix that captures the expected form of each of the 24 words. but they will recognize words. They'll recognize degraded forms of words, and they'll do better at doing so when they have matching prior knowledge. And so here's behavioral data from the participants in the experiment. So they're better at recognizing words when the speech is clearer or when they have matching text. Indeed, both the sharpening and the prediction error model, to optimize their parameters, can do a pretty good job of simulating that outcome. What do we get in the neural activity? Well, what we see is the same thing that was in the MEG study. So you see a reduction in neural activity when you have speech that follows matching text. So that's the same as in the earlier MEG study. If we make the assumption that the amount of time that the network takes to settle, so the challenge of processing the speech, is proportional to the bold response, then both the sharpening model and the prediction error model can capture that pattern of the magnitude of activity. So the reduction in the neural activity for matching trials is simulated by both sharpening and prediction error models. And what's more critical is the nature of the representations, and that's where those two models differ. So we're going to use our representational similarity analysis method again, applied to each of the 4 conditions. Here we're making the assumption that similarity will be observed for words that share the same vowel. So we'd expect thing, sing, and sit to have a similar pattern of representation, and that would be dissimilar from bath, path, and pass. When we go looking in the posterior STS, what we see is a interaction. So for speech that follows neutral text, so a row of X's, you get an increase in the amount of information in the neural representation in the posterior STS. Whereas for speech that follows matching text, you get a reduction as the speech becomes clearer. And so that perfectly corresponds to the simulation, the prediction that we would have generated on the basis of the prediction error model. It's very different to the pattern that you'd expect from a sharpening model. In terms of how prior knowledge constrains perception, we've seen that it enhances speech perception but suppresses the STG response. And it does so, it modulates pattern information as a function of signal quality in a way that seems to correspond to what we'd expected based on predictive coding. So hopefully time to just whiz through the third part. So, yeah.
How you want to use that information to help the patient?
It's a really good question. So obviously patients don't get subtitles on a day-to-day basis. What we know is that when they obviously listen with subtitles, the speech sounds clearer in the same way that it does for you. Assuming that you can generate a speech recognizer that copes better than they do in those challenging situations.
The subtitles come later than the
No. It was some data that it's what you need to get the benefit to clarity. So actually, it's a very time-limited process. So if the written word comes before the spoken word, that's fine. As soon as there's any delay between if the written comes after the spoken word, you get a very much benefit to clarity. And as soon as it's a second late, essentially there's no benefit to your subjective experience, so it's time limited. Well, it would be in the circumstance where you can delay the auditory input in order for it to catch up.
and other sounds want it to be real time. Sure.
This is where the third part, I think, is more useful to the cochlear implant user, which is that actually something that, sorry, Sophie, do you want to? Which is something that happens to cochlear implant users in the first few weeks and months of them using the implant, which is that their perception of speech gets better. They learn, they adjust to the sounds that are transduced by the implant. And that's something that we've been studying in the lab, something we term perceptual learning, so the way in which the perceptual system adjusts and tunes to degraded speech. In the context of cochlear implants, this is a form of auditory rehabilitation, and something that is driving the improvements that you see in their real-world speech reception. So we skip past that. Now, actually, we can see this in a very simple experiment. So those of you who struggled to make sense of the first vocoded sentence that they heard, don't worry, you're in very good company. So here's the data point from a group of healthy undergraduate listeners. So they also struggled to understand the very first vocoded sentence that they heard. But if you keep playing them vocoded sentences, each one different, over the course of 30 sentences, over the course of maybe 10 or 15 minutes exposure, they get better and better. By the end of 10 or 15 minutes, they might get 50 or 60% of the words in a typical sentence correct. Very good question, I'll come on to that. So in this experiment, they're not receiving feedback. What we've shown in a number of studies is that the more feedback that you give them, particularly those pop-out experiences, the more effective they're learning, the quicker that they learn. And so this is a study run by Alexei Hervé-Adelman as part of his PhD. So he played people single degraded words, got them to report, and then he gave them the clear and then degraded feedback, and compared performance. So this is giving you that pop-out experience, repeating that for 120 words and comparing it to a group of listeners that get exactly the same presentations but in an order that prevents them from getting the pop-out. So what Alexei showed, both in terms of word report or in terms of phoneme report, is that if you get those pop-out presentations, you learn more effectively, you learn more quickly. Now we have a whole bunch of other studies on this perceptual learning phenomenon that I'm not going to take you through in detail. But I'm going to summarize. So perceptual learning is supported by prior knowledge, so it's helped by feedback. It's not a form of rote learning. You're enhancing your perception of words and sounds that you've never heard in degraded speech before. And indeed, it generalizes to various transformations of the vocoder. In terms of neural activity, well, perception of degraded speech seems to be associated with this increase in frontal and motor regions. And actually, those frontal and motor region responses are absent if you're distracted or inattentive, but also perceptual learning is absent if you're distracted or inattentive. So we think that these two things go hand in hand, and hopefully I'll persuade you in the very last study that the top-down predictions from these motor regions are part of what's driving perceptual learning. It's another study led by Ed Sahoglu. It's again using MEG. The starting point is to take a bunch of listeners, put them into the MEG scanner, play them some degraded words and get them to report what they hear. They then get a period of training lasting about half an hour. They then do another test of their identification of degraded words. And we compare performance before and after. What you can see is for the 6 channel for these intermediate degraded words, they show significant improvements over the course of half an hour's training. There's actually quite a lot of individual variability, so some people get 20% better, some people struggle to improve at all. But on average, there's a very reliable improvement specific to this intermediate intelligibility condition. So if you have 1 channel vocoded speech, you never get anything from the auditory signal. If you have 24 channel speech, you're more or less at ceiling well throughout. Now, what sort of training did Ed use? Well, he used the written text followed by matching degraded speech that we've shown in a range of other behavioral work is a very effective form of learning. To make this training period interesting for the volunteers, he got them to listen to speech at a varying level of degradation to do the same rating task. He also gave them matching and mismatching text trials to replicate the earlier MEG study. And indeed it does, behaviorally and neurally. So you get enhanced clarity ratings for follows matching text. You get exactly the same changes in neural activity. So an increase in power for speech that's physically clearer, a reduction in neural response power for speech that matches prior knowledge. Again, that resembles that equation for predictive coding. So what happens what changes in the neural response from before to after? You might come up with 2 hypotheses. What are people doing? Are they extracting more information from the sensory signal? Is it a bit like adding more channels to the vocoder? Or are they enhancing their knowledge, tuning their perceptual system by having more specific expectations for what this form of degraded speech sounds like? Well, cut to the chase. The effect is a reduction in the MEG response that's specific to the somewhat intelligible condition. So in the 6 channel and in the 24 channel case, you get a reduction in the response that localizes to the STG. And it's consistent with the idea that they have more accurate predictions for the speech that they're hearing after training. Skip past all this. Both of those responses, so the the reduction in activity following learning correlates with individual variability in the amount of perceptual learning, as does the difference between match and mismatch trials. Sorry, I pointed the wrong way. That's the match minus mismatch neural response correlating with perceptual learning, and the pre to post training difference, again, correlating with behavioral improvements in our listeners. So again, Ed has a computational simulation of this, again, based on that same idea, so subtracting expectations from sensory signals. I'm going to skip past it. But the idea is that when you have matching prior knowledge, so you have an accurate target representation, the prediction errors that are generated in the superior temporal gyrus are a reflection not of mistaken identification, but of the discrepant form, and it's giving you a signal for what's changed in the degraded speech. And so this prediction error is what you should add to your connection weights in order to update perceptual processing. I've whizzed through that, I'm afraid. I'm happy to take questions. But that's the basic idea, is that what learning is doing in the system is to try and minimize the prediction error that you would experience the next time you heard a stimulus with the same kind of degradation. That's where I'll finish. Thank you very much to all the colleagues.